Continuing our discussion of the converse of the Pythagorean theorem, we have objective 2, where we're going to be able to classify triangles using that Pythagorean formula. What I mean by that is the converse of the Pythagorean theorem basically told us whether we had a right triangle or not. But what if c squared is not equal to a squared plus b squared? What kind of triangle do we have? So if you take a look at the image that we have here, in the background, dashed out, there's the right triangle. That's basically the a squared plus b squared equals c squared demonstration that we did in the previous lesson. And then what we have overlaid on top of it is either an obtuse triangle versus an acute triangle. We're going to take a look at this investigation here in just a moment. So we're going to do that specifically on GeoGebra. So in reference to the previous example, on the previous example, we had something like 5, 6, 61, or square root of 61, that made a right triangle. But we had 5, 6, 8. 5, 6, 8. What kind of triangle was that one? Because it wasn't a right triangle. And 5, 6, 7. That one was not a right triangle. So let's pull up my website here because I have a GeoGebra investigation already ready to go for this. So if you pull up Flippin' Math on Google Sites and we go to the geometry portal, the easiest way to get here is under the menu. We are under right triangles. This is the 3B here. So I'm going to expand this one out and you can see right there in the middle, 20-2 converse of Pythag. Let's load this thing up. All right, I'm going to scroll down here a little bit. And here's the GeoGebra investigation. All right. Now I'm going to do a couple of things here. I'm going to click on the settings and let's say zoom to fit. All right. And then also let's move some of this stuff out of the way. It says to drag point D to see what kind of triangle is formed when a squared plus b squared is not equal to c squared. I also have over here, here's our a squared plus b squared. Apparently it's equal to 40.5. And then actually let me maybe shrink this down a little bit so I can see full screen there. Everything that's happening. All right, there we go. So just like the picture for the objective, in the background we have in gray a right triangle, perfect right triangle with side lengths A, B, and C. And this area of polygon 2, this 9.9, that represents our a squared, which I can move around here. It is the pink square that's in the foreground, but it's also the grayed out one. Those two things are exactly the same size. It stays at 9.9, whatever 9.9 is. Okay, and then down here at the bottom, this area of polygon 3 is 30.7. That 30.7 is basically b squared, all right? And then I have two other measurements that are over here. Why are you on top of that one? There we go. I have area of polygon 1. Area of polygon 1, that's the one that's in the background. That's the grayed out one. That's the one that makes a right triangle. That's where we have our a squared plus b squared is equal to c squared one. And the one that's in the foreground here, this area of polygon 5, where's polygon 4? Who knows? That one currently 36.6. Now, whenever I move this this big dot for D, you can see that that thing changes. It changes the area of polygon 5. That's the only thing that it changes. It changes the type of triangle that I have when I use the lengths A, B, and C. All right. So over here to the left, when I move it, I have an obtuse triangle, obviously an obtuse triangle. And now compare these lengths, compare these squares. Here, for our polygon 5, which is our c squared, it's 63.5. That is definitely bigger than this 40.5 that c squared we would have gotten if it was a right triangle. Okay, so notice that that's always true when it's over here, when I have myself an obtuse triangle. As soon as I move it straight up and down, I have a right triangle. If I can actually get it right in there, it would be a right triangle where c squared would be equal to a squared plus b squared. And then any movement to the right here makes it an acute triangle. And now comparing our area of polygon 5, which is c squared, now it's definitely less than our right triangle that we would have gotten, which is a squared plus b squared. So to summarize this, if our c squared is bigger than a squared plus b squared, what kind of triangle do I have? I can see that I have myself an obtuse triangle. If I move it over here, if my c squared is less than a squared plus b squared, What type of triangle do I have? I have an acute triangle. All right, so let's summarize these things in two formulas, two theorems. The first one is called the acute triangle theorem, and the next one is going to be called, of course, the obtuse triangle theorem. So for your notes, if the square of the length of the longest side of a triangle is less than the sum of the squares of the lengths of the other two sides, then it is an acute triangle. Or you can just simply say, if c squared is less than a squared plus b squared, which is the c is always the biggest one, then the triangle is an acute triangle. So this is the whole entire reason why I want you to get into the habit of always writing the largest one first, the c squared down first, because it's very easy to relate this inequality sign to an acute triangle, right? It's less than. C squared is less than. I'm thinking acute. Acute is less than 90 degrees. It's very easy to make that association. If I flip this thing around, I would have a squared plus b squared is greater than c squared, and I might draw the wrong conclusion. I might draw the conclusion that I'm supposed to draw for obtuse triangles. If the square of the length of the longest side of a triangle is greater than the sum of the squares of the lengths of the other two sides, then that triangle is obtuse. In other words, if c squared, where c is the biggest side, is greater than a squared plus b squared, then our triangle is obtuse. Again, get in the habit of writing the largest one down first. That way I can easily associate that greater than symbol with the word obtuse. If I write it in the reverse direction, a squared plus b squared, for this one, a squared plus b squared would be less than c squared, and I might accidentally think that it's an acute triangle. All right, knowing that, let's go back to that previous example over here. This one here, where we were dealing with some numbers. On number 2, we knew that 5, 6, and the square root of 61 made a perfect right triangle because c squared was equal to a squared plus b squared. But on number 1 here, we concluded that c squared was smaller than a squared plus b squared. What type of triangle is it? Now we can conclude that this thing is acute. It's an acute triangle. All right? And then if I look over here at number 3, our c squared was bigger than a squared plus b squared. That's going to happen when we have ourselves an obtuse triangle. Excellent. All right. In the next video, we're just going to go over a couple of examples that's going to help us illustrate and work with these two theorems, the acute triangle theorem and the obtuse triangle theorem.